Thank you, Mark, and thanks to the SAEMC committee for giving me this opportunity. I think must mention the great thing about days like today for the technical community of South Australia is seeing progress on old projects you've been involved in and seeing new ideas and new concepts materialising and putting a future to some pretty interesting parts of South Australia. So well done, Ian and Mark, on that. So Cobra Resources, who are we and what are we doing? We're a UK main market listed company with a very strong South Australian based project focus, and over the last few years we've built a strong South Australian team to deliver this. What I'm going to talk to you about today is the process in which we've evolved and discovered a really unique ionic rare earth discovery in the Central Eyre Peninsula. So where are we? We're in the southern part of the Gawler Craton, south of the Uno Fault, where we initially started exploring in an earn-in with Andromeda Metals on the Wudinna gold project. Since then, we've significantly expanded our footprint in this pretty untouched and interesting part of the Gawler Craton. What have we focused on? Well, our work program has been fairly active on the ground over the last 3.5 years. Over that time, we've delivered over 109 line kilometres of geophysics of various forms, 12,000 metres of RC drilling, focused at expanding those existing gold resources at Baggy Green and Barnes, over 16,000 metres of air core, testing regional targets, both base metal and rare earth. And we've reanalysed, and it highlights the importance of things like the State Core Library, over 21,000 metres of previous historic drilling. And what do we think we've discovered? Well, we think we've got something pretty unique in terms of the Boland discovery. What's unique about it? Well, it actually doesn't fit the Chinese model for ionic rare earths. It actually occurs in Eocene age sediments of the Narrabee Paleo Channel. And we find that's interesting because there is potential to recover that via ISR. I'll go into some specifics on that later. You're probably all wondering, how do you plan on leaching clays? But due to the chemistry drivers for ionic absorption, we think we've got a good business proposition. What's significant about that style of mineralisation in South Australia is we are leaders in ISR mining. So not only do we have the skill sets and the regulatory framework to be successful in this, we believe that owing to the unique style of mineralisation we've discovered at Boland, we can provide a mine for the future that has very green credentials with minimal disturbance outputs. And that's something that we really want to be able to demonstrate in our work program going forward. How did we get here? Well, our initial focus was really on growing those gold resources. What we've defined over the last 3 years is a 40% increase in gold resources. So the resource now sits at 5.8 million tonnes at 1.5 grams over 4 camp scale deposits that are very shallow and amenable to open pit extraction. Whilst we're going through those reanalysis processes on a historic core, we identified anomalous rare earths that were above and proximal to the existing gold occurrences. And what we saw there was an opportunity in a commodity that is very challenging to be able to define viable economics, to be able to produce some value and a competitive economic advantage by defining critical minerals from overburden. And as such, we've developed a complementary resource that sits just under 42 million tonnes at 699 ppm TREO that sits directly above half of our gold resource. Now, how do we get from there to ionic mineralisation? I think what's important to note is with the clay-hosted saprolite ore that we have defined in our resource, the metallurgy is challenging. What we have at present, and what we've been able to understand through some excellent work and some great assistance from the likes of Laura Morrissey from University of SA, is we have a dynamic system and mobility of rare earths through that system. So what do we have and what do we know? We have primary enrichment of rare earth-bearing minerals in the alteration systems that are associated with the Hilderberg intrusives that occur with the gold mineralisation. Through some selective electron microscope or scanning electron microscope work that Laura did, she's been able to demonstrate that through the saprock profile, we have mobility of these rare earths to secondary phases, and then we have accumulations of rare earths higher up in that profile that have very little to no secondary or primary phase. So it mimics that model for ionic mineralisation that they see in southern China. MET testing, however, shows that a very small portion of those rare earths are ionically bound and can be desorbed as opposed to aggressively leached. So that put a basis for us that we knew that we had ionic or mobilisation of rare earths from enriched sources. So what did we need to understand to be able to identify areas that could retain ionic absorption over a geological history of 1.6 billion years? One bit of work that was critical to this, and Robert Blythman, our exploration manager, did some sensational work in compiling it, is we used very cost-effective pH soil test work to apply and create a significant data set with our rare earth assays to analyse what chemistry drivers are controlling the mineralisation. What did that work show? Well, it showed where we had depleted rare earths over the Barnes and White tank resources that sit at about 150,000 ounces. The acidity of the saprolite is less than 4 and sometimes as acidic as pH of 1. And we had rare earth enrichment at the Clark gold occurrence where the pH promoted grades that were elevated in the range of 6 to 7. So is this demonstrating a chemistry boundary? Is it redox? We certainly pondered a number of those sort of questions. And what was important is, and what we started to look into, is what chemistry promotes the hydrolysis of clays. So how do we accept that charge and increase the charge of clays to accept an ionically bound rare earth element? And if that's the case, can we domain mineralisation and grade by pH to increase the desorption capacity? MET testing results demonstrate a slight increase, but not materially significant. So then we started to ask ourselves, what environmental conditions are we missing that we need to identify the retained ionic mineralisation? And enter the Narrabee Paleo Channel. So what we were fortunate enough to be able to do on the back of the next speaker's previous work was to be able to identify anoxic and very reduced conditions within the Narrabee Paleo system. Not great for roll-front uranium, but perspective for ionic rare earth mineralisation, where what has essentially happened is we've had a catalyst of leaching that's been promoted by the enriched sulphides of the Hilderberg granites that's produced sulfuric acid that over time has leached those primary rare earth elements, and it's mobilised them and deposited them effectively in a cost-effective geological system that can be hopefully economically withdrawn. Here we have what we called the Boland Prospect. This sits in a very deep channel section of the Narrabee Paleo system. What we see over here is a typical profile of that system where we have very smectite-rich clays interbedded with very reduced lignitic coarse sands. And what we tested in our maiden drill testing in April of this year was a section of this system that is regionally significant. And what did the results show? Well, it showed that we had elevated rare earths within those Eocene age sediments. The grades relate to the clays, or more precisely, the contacts of the clays with the sands. Grades are reasonable, with elevated grades of up to 1400 ppm TREO, with an average of 24% magnet rare earth oxides, and we get a lot of variability in the heavy rare earth component. So that's showing that they're being mobile in this system. And what's important is we have strong enrichment of the saprolite peripheral and underneath it. So underneath some of those areas, we have up to 42 metres of saprolite that's going at grades over 0.2%. And what's excellent about ionic mineralisation is the recoverable ratio of light magnet rare earths to heavy magnet rare earths. So through our MET testing, we've demonstrated a recoverable ratio of under 7:1. What's important about this is if you look at market production at present, outside of China, we produce neodymium, praseodymium in excess of 100 per one quantity of diprosium and terbium. And forecast demand is more reflective of a ratio of 15:1. Okay, MET recoveries, rare earths is very important. This is the economic enabler to make viability possible for rare earth mining. What did our preliminary testing demonstrate to us? Well, we're getting strong recoveries of magnet rare earths and heavy rare earths under benign or relatively benign acidities over fast desorption periods. Magnet recoveries are up to 58% and heavy rare earths are up to 68%. What is most important about being able to leach in these benign acidities is the reduced dissolution of the unwanted gauge elements: alumina, iron, uranium, thorium. And what we're seeing in this paleo system is the dissolution of them is very low. What we're really encouraged by is the low acid consumption that comes with operating at those acidities. And if we look at our preliminary results, which are shown by the pie chart, the line graphs here, and benchmark them against what are optimised recoveries for two advanced projects ex-China, we're certainly in the ballpark of recovery potential. Why is pH important? Well, it drives the economics of costs through acid consumption and the complexity of the processing to refine and purify your rare earth product. And if you look at where we're operating, we have an aquifer that currently sits at a pH of 5, same equivalent of acidity as your coffee. And what we're hoping to do through ISR is to drop it down to a pH of 3 to be able to mobilise those rare earths and bring them to surface. And what's important there is the associated environmental risk operating in those conditions is much lower than dropping acidities to aggressive leaching. And what we believe is obviously environmental risk increases, but so does the operating cost, and that's our opportunity. Now, why don't we think we need to leach the clays? Well, ionic rare earth absorption is promoted by changes in chemistry. And we've done this initial test work over 3-metre composites. We know through our downhole pH testing that the greatest changes in chemistry occur on the clay-sand boundaries. So, if we can demonstrate that we can utilise the permeability of the paleochannel sands, we think that via in situ, we can get high recoveries of more concentrated grades on those clay-sand contacts. What's our opportunity and how are we going to bring this project forward? Well, I think what we need to do is we need to look at what the industry challenges are. Rare earths are a complex game, and whilst there's been a lot of macro interest in the industry, we haven't seen a lot of projects materialise. Why is this? Well, generally, most advanced projects in Australia and abroad are large. They're significant projects requiring significant capital outlay to be able to bring them into production. And if you look at this graph, which is just a cross-section of the number of advanced companies that are at definitive feasibility stage or financing, their CapEx requirement is disproportional to what their equity and what their potential debt enabling ability is to finance that project. So from a financing perspective, financiers don't find the right palatable blend to be able to progress those investment decisions. And here lies our opportunity. ISR, by a number of people in this room, has been demonstrated to be far less capital intensive and far less cost intensive operationally. And so we believe that if we can demonstrate via ISR a very low cost and viable recovery method, we're going to be competitive in this market. How are we going to do it? Well, as with every good mining project, more drilling. And what we hope to do over the next 12 months is really de-risk that ISR component of this discovery. So early next year, we plan on executing a sonic drill program. This program, we hope, will enable us to perform the hydrology studies to be able to support future pilot testing. And then we also want to be able to demonstrate ISR at a bench scale. So through a partnership with a group called Water Cycle Technologies, we are aiming to be able to devise a cost-effective flow sheet through selective membrane desorption. And one thing that we're very excited about is to be able to test the opportunity to produce our own acid from the organics that sit within this aquifer system. If we can produce our own acid on site through the preconditioning processes of ISR, that gives us an extra advantage to be able to reduce our operational costs. What do we see in terms of this as an opportunity? We don't see this as being an opportunity just for Cobra. It's an opportunity for South Australia. We're a tier 1 jurisdiction that are leaders in ISR. And we really see that we can apply those skill sets that has successfully executed projects in uranium and making this applicable in the critical mineral sphere. And what we hope to do through this work is to be able to produce a new industry that will enable the state to be able to align itself with its energy ambitions and decarbonisation strategy to be able to produce critical minerals for decarbonisation. What we're really keen to be able to do from a stakeholder perspective is to demonstrate that this method of mining with this style of mineralisation that can be quickly desorbed can be integrated into current land practices. So that's work that we have planned, and hopefully when we're here next year we can show some material progress in what we think we've discovered here. All right, thanks Mark.